A ni set trigger alarm, for alarm. Kat sini. Untuk gas detector, kalau detect gas 60%, ada omega, ada alarm gitu. Kalau untuk yang 20%, ada kalau fault, ada kena set. Ini contoh lah. Kalau kita pergi part lain, mungkin ada lain lah. Tapi konsep asal memang macam tu. Okey, contoh saya ni, kita nak mouse tadi yang saya tak tulis tadi. Basically yang ni dekat DCS.
I find smoke detectors a marvel of engineering. Let me show you how it works. This black cylinder has louvers which guide air into the detector. Now it hides the essential part of the device. Tucked in here lies about 1 microcurie of radioactive americium-241. That's about 0.29 micrograms. That tiny bit of radioactive material generates a small current that makes the detector work. Let me explain how. Air flows between these two electrodes. Now, of course, air doesn't conduct electricity, but when alpha particles from the radioactive americium slam into the oxygen and nitrogen molecules that make up air, they knock electrons about, leaving charged gas molecules. The 9-volt battery causes these ions to move, thus creating a current. Now, here it's tiny, something like 100 picoamps, about 100 billionth the current flowing in your home. When smoke enters the chamber, the ions attach to it and slow down and often lose their charge. Both events cause the current to stop, which triggers the alarm. Now, to make such a compact thing work with only a 9-volt battery required the solid-state revolution of the 1960s. Let me show you. If I remove the two electrodes, you can see a small integrated circuit. It incorporates a marvelous device called a MOSFET, which can detect those very small changes in current. In the detector, it serves as an on-off switch triggered by the tiny current between the electrodes. Like every transistor, its operation depends on being able to make diodes from semiconductors. Recall that a diode allows current to pass in only one direction because it uses two types of semiconductors, a type that uses negative charge carriers and one that uses positive charge carriers. Flip that battery and the flow of charge stops. Now, to build a MOSFET, we take two such diodes and put them together so that each is reversed. Now, this seems useless because no current will ever flow through such an arrangement, but engineers embed this diode sandwich into the same type of semiconductor as the diode ends that touch. Then they place metal contacts at the ends of the diodes and on the block of semiconducting material. Next, they coat the diodes with a thin layer of silicon dioxide. Unlike metals or semiconductors, this doesn't conduct electricity at all. On that, they place one more metal contact called the gate, which opens or closes the current channel between the source and the drain. When we create a voltage difference between the gate and the source, it generates a field through the insulating layer that draws the free positive charge carriers toward the gate, opening a channel that now allows current to flow. In a circuit, we use the 9-volt battery to generate a potential difference between the source and the gate. It biases the gate so that the current flows through the MOSFET, thus turning on the horn. So we counter that with a current flowing from the detector. Here is where the ionized gas creates the tiny current between the two electrodes I showed you earlier. That current passes through a large resistor and creates a voltage that opposes the battery, and it shuts down current flow through the MOSFET. If smoke enters the chamber, the tiny current stops. The MOSFET allows current to flow in this section of the circuit, which triggers the horn. Now, to me, this is engineering at its best. Simple, reliable, and inexpensive, saving countless lives. I'm Bill Hammack, the Engineer Guy.